Hi. In the previous video, I did an example where none of the three conditions is satisfied. And I told you there are many such examples where none of the three conditions will be satisfied. So my question in this example, in this video is there a condition that you can check to see if the extremal type theorem will hold or not? In other words, is there just one condition instead of three conditions? Is there one condition you can check to see that none of the three conditions will be satisfied? The answer is yes, right? Before I do that, before I give you the answer, let me write down something. Checking So the checking of the three conditions can be time consuming, especially in an exam. If I give you a problem and ask you to check the three conditions, then and you spend you lose time. Especially if that problem is one where none of the three conditions is satisfied, then you'll be spending minutes checking each condition separately and find out that none of them are satisfied. So in such situations, it's easy if there is just a single condition. If there is a single condition that you can check to see if extremal type theorem will hold or not, right? Okay. Right. Okay. So what I'm saying is that it's useful to have a single condition to say that the extremal type theorem will hold or not. So if that single condition is not satisfied, then that means that none of the three conditions will ever be satisfied. And if that single condition is satisfied, then you can be confident that one of the three conditions will be satisfied. Okay. So right, suppose x is a discrete random variable with CD of f, and let w of f denote its upper endpoint. Then then the extremal types theorem will hold if and only if the following condition is satisfied. Okay, so if this condition is satisfied, then one of the three conditions I mentioned in my previous videos will be satisfied. And if this condition is not satisfied, then none of the three conditions in my previous videos will be satisfied. Okay guys, so now let's do some examples. But you can only check this if when x is a discrete random variable. Okay. So let's start with example 1. IID, I mean, if you don't know what it means, is independent and identical geometric random variables with parameter p. The question is, does the extremal types theorem hold? Right? Okay. Now, for the geometric distribution, I'm sure all of you may know. If you don't know this, just note this down. The probability mass function for a geometric distribution is p times 1 minus p to the power k minus 1, where k can be take any values 1 to up to infinity. Okay. W of f in this case is because k can take any value from 1 to infinity, the largest value of the support. Remember, the support is the set of integers from 1 to up to infinity. So the largest point of the support is plus infinity, right? So W of f is plus infinity. So now let's check the condition from the previous slide. This is the slide I showed you. So I'm going to check this condition now. Okay. So this is going to be the limit of the probability x equal to k divided by 1 minus f at k minus 1. So this is going to be the limit as k goes to infinity of and 1 minus. Now for the geometric distribution, the CDF, if you don't know this already, the CDF for a geometric distribution is 1 minus p at k minus 1. Right? So the two ones cancel out. So you get this to be the limit as k goes to infinity, and this is clearly equal to p, and p cannot be 0. So hence so the extremal types theorem fails to hold. In other words, none of the three conditions that I mentioned in my previous videos will ever be satisfied for this example. Example 2. Suppose, so all the examples I'm doing are discrete examples, because the condition I gave you applies only for discrete random variables. Right, so this is here we are assuming that the random sample is from a binomial distribution with parameters m and p. I'm sure all of you guys remember this distribution from your first year. So for this distribution, the probability mass function is okay. Right, and you can see clearly this is the support of the distribution, and the largest point of the support is m. So hence the W of f is equal to m. So the condition that we need to check is the limit as k approaches m of the probability that x equal to k divided by 1 minus f k minus 1. Alright, so since m is a finite number, this will be simply the probability that x equal to m divided by 1 minus okay. So the CDF at m minus 1 is simply, by definition, is the probability that x is less than or equal to m minus 1. Now 1 minus this probability is simply the probability that x is greater than m minus 1. Now if x is greater than m minus 1, the only possible value it can take is the value that x is equal to m. Right? So hence this is equal to 1, and this is clearly not equal to 0. Right? So hence, since the limit is not equal to 0, once again the extremal types theorem fails to hold. All right. I'll just do one more example. So this will be example number 3. Suppose so we have a random sample from this distribution where the probability mass function is equal to 1 divided by capital N for k from 1 to capital N. And this distribution, if you don't know already, this is known as the discrete uniform distribution, right? So the question is once again the same. Does now from the PMF you can see clearly that the largest point of the support, this being the support, the largest point of the support is N. So hence the upper end point is equal to capital N. Right, so the condition we want to check is whether the limit of this is 0 or not. Right, so because capital N is a finite number, this is the probability that x is equal to capital N. Okay, and this you can write as the probability that x equal to N. Probability that x is less than or equal to n minus 1. Okay, that's by definition of the CDF. This is equal to this. Okay, so this is the probability that x is equal to n divided by 1 minus this is the probability that x is strictly greater than n minus 1. Now, if it's strictly greater than n minus 1, then the only possible value it can take is capital N. Okay, so this is clearly equal to 1, which is not equal to 0. Hence, so